Good morning, guys. We are going to go over chapter 4. And I need you guys paying attention because I'm going to have an exit ticket that uses some of the concepts. So we're going to try to focus on solutions and solving some problems with solutions where you're given the volume, um, maybe the molarity or the concentration of a solution, and then you've got to do some calculations. We're going to try to keep this to an hour. I'm actually going to time myself because there's a lot of slides here, and I'm basically just going to set the timer and then go from there. So I'm going to set my timer, and we're going to go through this. We're going to do this chapter for 2 days. So this chapter goes through solutions and solution stoichiometry. It gets into solubility and how things dissolve and ionic equations, not ionic equations. Then it goes through every type of reaction. So you talk about synthesis, decomposition, combustion, oxidation, acid-base reaction. So it goes through all the reactions. So there's a lot in this chapter. But we'll start with the first steps, okay? This is chapter 4. We're still in unit 1, which is kind of reviewing stuff. You should have seen this in your first year course. Some of this might be kind of AP, but kind of not, but it's pretty critical for a lot of stuff that we're going to be doing. All right, so think about the water molecule. Here's a picture of water, cute little H2O. He's just hanging out. He's got 1 oxygen and 2 hydrogens. All right, and this diagram is showing the polarity of the molecule, okay? So here's the bond angle between the hydrogens. It's 105 degrees between those hydrogens, and we'll talk about why that is later. These are partial charges. So there's a partial positive charge. This is the symbol delta. It's a Greek letter, so that's the symbol for partial charge. So there's a partial positive charge on hydrogen and a partial negative charge on oxygen. And the reason for that is because oxygen is electronegative. Oxygen is in group 6, and so he is extremely electronegative, right? Think about oxygen. Let me pull up a periodic table here. Where is my periodic table? Should have pulled this up before doing this. Okay, so oxygen has 8 electrons. So 2 in the first shell, and then the second shell has the remaining 6 to make a total 8. And the nucleus is right there in the middle. All right, and so it has 6 electrons in its outer shell. It wants 2. So what does it do? It finds a hydrogen with 1 lonely electron hanging out, and it's going to pull it to him. It's going to take another hydrogen with 1 lonely electron, both of which want to give up their electrons because this hydrogen kind of behaves like a metal. So he wants to give up his electrons to oxygen. So oxygen's going to take them, and it's going to take them kind of violently. And so it pulls those electrons to oxygen, and oxygen is not going to share them. Oxygen is a bully. So oxygen will pull those electrons. We call this electronegativity. It's a tendency of an atom to pull electrons to itself so that it basically hogs the electrons. All right, and so since it hogs those electrons, the electrons will spend more time around the oxygen, and it'll create a partial charge. So at any one time, oxygen is kind of holding more electrons than hydrogen is. And so oxygen has a partial negative charge, and hydrogen has a partial positive charge. So if you have several water molecules hanging out, so here's one, and let's take another water molecule and put him in here and see how he's going to arrange. And what he's going to do is the hydrogen is positive, the oxygen is negative, so these are going to attract. All right, and that's actually called a hydrogen bond. And it's a slight attraction. It's enough for the molecules to kind of stick together. And this is why water has all of its neat properties, right? Bugs can walk on water because of hydrogen bonding. There's a lot of cool stuff with hydrogen bonding, and then we'll hit that in another chapter. But we want to talk about why water is such a good solvent. And the reason for that is because it's polar, because oxygen is extremely electronegative. All right, and when we say polar, we mean that this side of the molecule is negative, and then this side of the molecule is positive, and that's a separation of charge. And so that's called polarity. All right, so since water is polar, it's very good at dissolving stuff. All right, if I take some sodium and put some sodium in some water, it's going to dissolve and mix with that water. These are the lone pair electrons on the oxygen. See how it's hogging the electrons? So if I put sodium in here, it's got a plus charge. Well, the negative charged oxygen is going to kind of pull that sodium in, and it's going to form an ionic bond there between those two. And the hydrogens are positive, so they're going to repel the sodium. They're going to want to repel as much as possible. And then the chlorines, if I had sodium chloride, NaCl, the chlorine is going to want to come in here and attract to this slightly positive hydrogen, and they're going to want to hang out together and form an ionic bond. And this is how things dissolve. Remember that this is a physical change, dissolution. Okay, so this is kind of how things dissolve. This uneven distribution of charges makes water polar. Because of this, water is a good solvent. It's actually called the universal solvent because it dissolves most stuff. And we've talked about this stuff. Positive hydrogen attracts negative ions or the negative end of another polar molecule. And then the negative end of water, the oxygen, will attract the positive ions or the positive end of another polar molecule, like the hydrogen atoms on a water molecule. When water surrounds an ionic crystal, the hydrogen end attracts the negative ion and attracts the positive ion. This is called hydration. It makes hydration spheres. All right, so hydration causes salts or ionic compounds to dissolve. Water also dissolves polar covalent substances such as alcohol. This is ethanol. I think let's see, C2H5O8. Yeah, this is a type of alcohol. Water doesn't dissolve nonpolar covalent substances because there is not enough attraction between water and the nonpolar molecule. So it'll dissolve polar substances, polar covalent substances like an alcohol. And the reason that this is polar is because of this right here. This is partially positive, this is partially negative. And so this part of the molecule has a charge, and this part of the molecule really doesn't. So that's a polar covalent molecule, meaning that it will dissolve but not break up. It'll maintain its structure. So that's kind of cool. Sugar does the same thing. Sugar is a covalent substance that will dissolve in water, but it does not break down into ions. It keeps its structure, but it still dissolves and mixes with water. Obviously, you take sugar, put it in water or coffee, and mix it, and it'll disappear and dissolve, right? Yeah. So here's a picture of hydration. So if I take some salt, let's take a salt cube and put it in water. The water will attack it. And because of the polarity difference, water is going to attack the negative ion, and all of the hydrogen is going to surround it and make a hydration sphere. And it's going to separate this. This would be chlorine if this were sodium chloride. So the white ones are sodium, the green ones are chlorine, right? And so all of the hydrogens are going to surround this chlorine negative, and it's going to make a hydration sphere. So it's going to separate the sodium and the chlorine from each other, right? And then down here, we've got all of the oxygen sides of the water molecule attracted to the sodium. Okay, and we need to be able to draw these pictures showing water attacking these ions. This is pretty common. This is pretty commonly seen on the AP test, drawing these pictures. All right, this shows the association of the ions. So this is how they're arranged. Hydrogen is positive because it's electropositive. It's on the side of the periodic table with the metals, right? If you look at the periodic table, hydrogen is over here with the metals, so he's electrically positive. These are electropositive, meaning that they tend to want to lose electrons, which makes them positive. And then over here, fluorine and oxygen, these two groups, and up in this corner are very electronegative. All right, these guys are not either. These are noble gases. They don't react. So remember that this is kind of the extreme right here for the negative side of things on the periodic table, and then down here is the extreme for positive. Most reactive, most reactive. A solution is a homogeneous mixture. In a solution, a solute dissolves in the solvent. So the solute is what is in smaller amount, and it will be mixed into the solvent. If the solute ionizes and forms ions in the solution, it can conduct electricity, and we call it an electrolyte. Okay, if it dissolves completely, like 100%. So if you take, for example, HCl, which is hydrochloric acid. You take this stuff and you put it in water. It's going to make hydrogen ions and it's going to make chlorine ions, right? So imagine that this is a molecule together. This is actually a covalent molecule, right? Because hydrogen's a nonmetal, chlorine's a nonmetal, and they're sharing electrons, okay? So they're sharing electrons hanging out. You put this guy in water, they split up, okay? And if you look at a beaker of this stuff after this is done, you're going to have all hydrogen and chlorine ions. You will not have any of the HCl remaining together as a group bonded, covalently bonded. It's going to break up completely. So we call that 100% ionization, and we call it a strong electrolyte. If they do not disassociate or ionize completely, we call them weak electrolytes. And that means that some of it's going to break down and some of it's not. And so it's actually going to be an equilibrium, which we'll be talking about. All right, a solution, this is kind of a repeat of some of the stuff. An aqueous solution is where water is the dissolving medium, or water is the solvent. Electrolyte is any substance that conducts electricity. Here's a couple examples. I think that's why I kept this slide, is I like the examples, as opposed to non-electrolytes, which are usually sugars. They will still dissolve, but they don't produce ions in solution. If you look at these guys, when you put these guys in water, they're going to make ions. That's going to be H with the +1, chlorine with the -1, sodium with the +1, chlorine with the -1. This is going to be potassium, and then this OH is going to stay together, but it's going to be a -1. So it's going to be O and an H, and it's going to have a -1 charge, and it's going to stay together. It's going to look like that. Okay, and then sugars are non-electrolytes, meaning that they dissolve. They are soluble in water, but they do not produce ions with charges. So they do not conduct electricity. Or alcohols. Alcohols or sugars are non-electrolytes. And again, I showed you guys why the alcohols are soluble. And that's because they've got electrons on these oxygens. And so that's negative, partial negative, and the partial positive right there. Partial negative, partial positive. And the sugar is kind of the same thing, the negative, and the side of the molecule is going to be positive. And so that polarity will allow it to dissolve into water. Okay, solubility is the ability of a substance to dissolve in water. It is usually written as grams per volume or moles per given volume. So it could be grams per milliliter. It could be grams per liter. It could be moles per milliliter. It could be moles per liter. So this is solubility. So this is like the unit for solubility. Solubility is how much something will dissolve. So we use the how much. It can be grams, which is mass, or it can be moles. Either way, it's how much, and it's divided by volume. So that's solubility. As a general rule, ionic solids will break down or disassociate into ions when they're put in an aqueous solution, so when they're put in water. The partial negative charge and the partial positives will allow water to strongly interact with and pull out the ions in the crystal lattice. So ionic compounds like sodium chloride, potassium fluoride, sodium hydroxide. These are all strong ionic compounds that make strong electrolytes. Excuse me. So, see how the waters will grab that H plus or whatever this positive ion is. All right, for molecular compounds, the structural integrity of the molecule is maintained. Substances may dissolve, but they won't split up into ions. So these are called non-electrolytes. Now there are exceptions. These are molecular compounds or covalent compounds where it's all nonmetals. All right, so you've got sugars and alcohols that will dissolve. There are two exceptions. One of them is called an acid, which we'll learn our 7 acids, and then ammonia. These are covalent compounds, right? HCl is hydrochloric acid. Notice that it's hydrogen and chlorine. If we look at our periodic table again, hydrogen is right here, non-metal. Remember, hydrogen's a non-metal. He's over here with the metals, but he is a non-metal. And then chlorine's right here, non-metal. So two nonmetals hanging out, it's definitely a covalent compound. And it is a strong electrolyte, so it's an exception. Most covalent compounds are not strong electrolytes, but acids are, because acids break down in water. And then ammonia is a very common one. And the reason ammonia is because it's got lone pair electrons on that nitrogen, making it polar. So the nitrogen will have a slight negative charge, and then the three hydrogens will have a slight positive charge. So that's going to create a polar molecule where this side is negative, this side is positive. And so then it'll interact with water and be able to dissolve. When molecular compounds do split up, we call it ionization. So when an acid breaks down, or when a sugar dissolves, or when an alcohol dissolves, or when ammonia dissolves, we call it ionization, not dissociation. Okay. Strong electrolytes include soluble salts. So any kind of substance, any kind of ionic substance that is soluble. So that would include sodium chloride, potassium fluoride, sodium hydroxide, and we'll talk about these, but there's many, many more examples, but here's a few. And then there's strong acids, which completely dissolve. So any of our strong acids, hydrochloric, nitric, or sulfuric. And there's a few more. There's 7 strong acids that we'll talk about. All right, so this picture shows how hydrogen, you can call it hydrogen chloride, is what I guess it would be called, but since it is an acid, we would name it as an acid. So it's hydrogen chloride if it's in a gas state, but if it is in a aqueous solution, if you put this in water, it's going to be called hydrochloric acid because it acts like an acid when you put it in water. So I've got HCl, so H is the green, Cl is the minus. The negative ions are always bigger. Okay, nonmetals get bigger. Metals are kind of small, typically when they're in solution or when they're wet. Well, pretty much anytime. Anytime a nonmetal is usually bigger because they got more electrons, and all those electrons will repel each other, and so they kind of balloon up. So that's why nonmetals are bigger. So if you take this guy, put it in water, it's going to ionize. It's going to mix with water. So water is going to surround this guy. Water is going to surround this guy, and they're going to be separated in that solution. Notice we started with molecules, right? We started with HCl. And look what we have. Here is the minus chlorine. Here's the minus chlorine. Here's the minus chlorine. Here's the positive. Notice how they're all separated. That's what we mean by complete dissociation or complete ionization. That's a strong electrolyte or a strong acid. Breaks down completely into ions. All right. Oh, and I had the equation here. So this is the equation for this picture. HCl breaks down to H plus Cl minus. Okay. And at this point, if you guys see a one-way arrow, that means that it breaks down completely. It's one direction. There is no going back. Okay. So if you see an arrow like that, it typically means that it's one way. And there are times where it's a two-way arrow where it does go back and forth, and we'll talk about that. So strong acids and ionic substances like this will completely ionize one way and no going back. That's what that arrow means. All right, acids are substances that produce H plus ions in water. So if you take an acid like HCl, we know that if you take HCl and put it in water, it will form H plus ions, chlorine ions, and then you'll still have water in there as a liquid, and it's going to mix up all those ions. It's going to dissolve them. All right, so we call this an acid, and this is an Arrhenius acid, which we'll have a whole chapter on acids later. All right, strong bases also ionize substances completely. All right, a strong base is any group 1 or 2 hydroxide. So group 1 or group 2 metals, when combined with the hydroxide ion, so this is hydroxide. So when you take a group 1 metal or a group 2 metal and add them to hydroxide, like these two examples, you get a strong electrolyte and you get full ionization, 100% breaking down. And these are dangerous, right? Bases are dangerous. They taste bitter and they have a slippery fill, and you can find them in soap, and that's why soap is so good at cleaning. It's because it breaks down substances. All right. Weak electrolytes only slightly ionize. So I'm going to actually redraw this arrow as this. And it means it goes both ways. So some of this molecule will break down. It'll interact with water a little bit because it's a little bit polar, but most of it will stay over here. So if I looked at a bottle of this, if I looked at the ions and I zoomed in with the microscope to look at it, most of what I would see would be still this. I wouldn't see a whole lot of the ions. So maybe 1% of it would break down into ions. The remaining 99% would still be in this form where it's not splitted. So we call that a weak electrolyte. So they only ionize slightly. This is acetic acid, I believe, which is in vinegar. All right, so this is what we would see if we zoomed in. We would see the complete molecule. And then, oh, here is one positive ion and one negative ion. And so one of these guys broke up. That's it. So 1%. Strong let's see. So this is kind of the same thing. Here are some examples of strong electrolytes. Notice that there's lots of products. And so 99% would look like this. Notice it's a one-sided arrow, not a two-sided. Weak electrolytes produce only small concentration of ions, and they are going to cause equilibrium to happen, which means that as soon as this guy breaks down, it's going to form these ions. These ions are going to find each other, and it's going to quickly go back the other way. And so that there's no net change in the concentration of any of the stuff in this reaction. So I've got, let's say if I got 10 molecules of this, okay? So at one moment in time, those 10 molecules, or let's say one of the molecules might break down. So I take one molecule, and it'll break down according to this equation, right? So only one will break down. These two guys are hanging out in the beaker. They will find each other, and they will reform this guy pretty much as soon as they form. So as soon as you form them, they combine back and produce the reactants. And so there's no net change in the concentration of anything in the reaction, because as soon as you form it, it goes back the other way. So this is a weak electrolyte or a weak acid. There's two examples. So lots of reactants. So if you were to zoom in and look at the beaker of this stuff, you would see mostly this. You would not see much of the ions, maybe 1%. Notice it's a double arrow. All right, ammonia is a weak base. And so if you take ammonia and add it to water, it's going to make the ammonium ion. I hope you guys know this ion, ammonium. And I wish we had more time to spend on the ions, because I would love to do like a ion review and then like a quiz and get you guys up to speed on the ions. But I feel like it's just a little bit better to just kind of see this stuff over and over again. And I mean, you see it enough to where you get tired of looking it up. That's how I did it when I first started teaching chemistry, is I just got tired of looking this stuff up. So I just kind of memorized it over time, and hopefully you guys will do the same. So that's ammonium, and then this is hydroxide. So this is a weak base, which means that if you looked in the container, it would be mostly this floating around in the beaker and not much of NH3 in water. Okay. Some of the strong electrolytes are strong acids and strong bases. All right, so here are our 7 strong acids: hydrochloric, hydrobromic, hydroiodic. And these guys are hydrogen combining with a group 7 halogen. Group 7 halogens are right here: fluorine, chlorine, bromine, and iodine. There's another one, but it doesn't really matter. These are the main ones. So fluorine, chlorine, bromine, and iodine are group 7 halogens. They have 2 electrons in their first shell, and let's see, 7 electrons in their second shell. Okay, and so they want 1 more electron. They need 8 to fulfill their outer shell. And so they're going to pull in one electron to themselves very violently. And where are they going to find that one electron? Poor, unlucky hydrogen. It's got a positive one charge. He's going to pull that hydrogen to him. And so HCl plus water will make hydrogen ions and chlorine ions in solution, where they're dissolved in water like we've been showing. There's a couple other ones. There's chloric, which is hydrogen and ClO3, the minus charge. That's the chlorate ion. So chloric acid, chlorate to chloric. There's perchloric. The perchloric ion is ClO4. And so if you add hydrogen to it, it's perchlorate, and it turns into perchloric acid. Nitric acid has the nitrate ion in it. You add hydrogen to it, and you get nitric acid. And then sulfuric acid has the sulfate molecule, or sulfate ion. You add hydrogen to it, and you get the sulfuric acid. So these are our 7 strong acids. All right, hydrochloric, hydrobromic, hydroiodic. Remember, these are our 4, 1, 2, 3. Actually, fluorine doesn't count, and there's a reason for that. But chlorine, bromine, and iodine all form strong acids. But fluorine does not, and I'm trying to remember why. I think it's because it's too electronegative. Because HF is so strongly held together that it does not fall apart in solution. So it's a weak electrolyte. But chlorine, bromine, and iodine are all strong electrolytes. And then you got chloric, perchloric, nitric, and sulfuric. And these are all going to break down 100% in solution to make strong acids. And the definition of a strong acid is a substance that breaks down completely. It doesn't necessarily mean that the acid is dangerous. All acids are dangerous. But when we say strong acid, we don't mean more dangerous. We mean that it dissolves 100% completely. Okay, let's clean this up. Strong bases are the hydroxides of group 1 and 2 metals, like I said before. So group 1 or 2 metals with OH, and you get strong bases. All right, be careful to distinguish between dissolution and dissociation or ionization in regard to strong or weak bases. For example, this alcohol, or what's this alcohol? This is a carboxylic acid. So this is, what is this guy called? Acetic acid? C2H4. I'm trying to remember what this guy is. This might be an alcohol. So this guy, no, it's not an alcohol. This is maybe acetic acid. So this is acetic acid, I think. So acetic acid dissolves completely, but ionizes only slightly. It's therefore a weak electrolyte. On the other hand, barium hydroxide dissolves very little, but the amount that does dissolve disassociates almost completely. So barium hydroxide is a strong electrolyte. So just some clarification there is. The question is, of the amount that dissolves, what fraction actually ionizes? And that tells us whether it's a strong or weak electrolyte. If it's most, it's a strong electrolyte. If not, it's weak. All right, molarity is a way to measure the concentration of a solution, and it's like how much is in there. So if I'm dealing with an acid, molarity would be a way to represent how much of that acid is in there, right? Because you're mixing something with water, but how much is in there? Molarity is capital M, and it's one of many ways to measure concentration. It is the moles of the solute, which is what we're dissolving, divided by liters of solution, which is going to be usually water. All right. We can also do molarity in millimoles per milliliters of solution. So we can do moles per liter. So if I had sodium chloride, it would be moles of sodium chloride for liters of water per a liter of water. So how many moles of sodium chloride are in the solution per every 1 liter of solution? So that's 1 liter on bottom. Or we can do moles, millimoles, which a millimole is a 1,000th of a mole. So a millimole divided by a milliliter solution. We just divide the top and the bottom by 1,000. We divide the moles on top by 1,000. We get millimoles, which is 1,000th of a mole, and then we get milliliters on bottom. And sometimes that just makes it easier for us to calculate things. Molarity is very common. There's also something called normal, which is another way of doing it, and it's capital N. We don't usually use it in AP chemistry that much. It's kind of an old concentration. There's also percent. You can say, okay, it's 50% acid, right? So percent concentration by volume could work as well. But we usually use molarity. That's our favorite. All right, so let's calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. All right, and I hope you guys are still paying attention to these notes. Like I said, we're going to have an exit ticket where I'm going to be pulling these questions, okay? And I know these videos are long, and I apologize, but I do try to make them kind of exciting and, yeah, as much as I can, because I'm excited about the chemistry, and I hope you guys get excited about the chemistry. So let's calculate this one. So we have 23.4 grams of sodium sulfate. All right, sodium is Na, and sulfate is SO4 with a 2 minus. So sodium is in group 1, and y'all remember our charges? If I draw the periodic table, here's groups 1 and 2. Remember, group 1 forms +1 ions. Group 2 forms +2 ions. Group 3, the boron family, +3. Carbon family is plus or minus 4. All right. Nitrogen is -5. Oxygen, -3. Wait. Nitrogen. +3, -4, I'm drawing a blank here. I know oxygen is -2, so I guess it's -3. So it switches from positive to negative. So group 3, the boron aluminum family, is +3. Carbon is plus or minus 4, but then it goes to nitrogen, which is -3, and then -2 for oxygen, and then -1 for the halogens, which is fluorine, chlorine, bromine, iodine, the halogens. And then the next one is 0. Helium, neon, they don't make charges. All right, and sulfate is just an ion that we have to know. Sulfate is SO4 with a -2 charge. So that's our compound there. We have 23.4 grams of sodium sulfate. Sodium is a +1. Sulfate is a -2. And so if I put them together, all right, I got a +1 on this one. I got a -2. So if I had these two together, I would have a net negative charge. I would have one more negative than positive, and I can't do that. So I have to add one more sodium to make it balance. So the formula for this is Na2SO4. Okay? So we have 23.4 grams of this stuff. We're going to need to take that and divide it into the molar mass. All right, so 23.4 grams divided by the molar mass right here. And that'll give us 1 mole of this substance, Na2SO4. All right, and then once we have moles, we can divide by the volume. This is milliliters, and we want moles per liter, right? We want molarity, which is going to be moles per liter. So what I'm going to do is I'm going to take 125 milliliters. That's 1,000th of a liter. So I need to move my decimal place 3 places to the left to get it into liters. 1, 2, 3. That's 1 mole. Let's see, that'll be 1 mole. This part's tricky here. I remember this part. I need to divide by the volume because I know because now I got moles, and I know I'm not showing the mass yet. I'll show that in a second. So the mass would cancel here. I got moles of this stuff divided by volume. So this would be 0.125 liters, or 125 divided by 1,000 to get it into liters. And I just put a 1 on top. And I know that's weird, but you need to divide moles into volume, moles per liter. So that's what I did. And we should get our answer. So let's see what we get. All right, the molar mass of this stuff is 142.06. I get that from the periodic table, adding up the mass of 2 sodiums, 1 sulfur, and 4 oxygens. I get 142. I know that 1 mole of that stuff is that much weight. So now I have moles. That's 0.165 moles of the stuff, and then I divide it by liters. And it might be easier to do it this way. I do it all in one step on the dimensional analysis. You can totally do it this way. You can take the mass divided by molar mass and get moles, and then divide by volume in liters. Remember to put it in liters, and then you get the molarity. So this is 1.32 molar, or 1.32 moles in every 1 liter. Okay? Fun. How many grams of sodium sulfate are required to make 350 milliliters of 0.5 molar solution? Ugh. Okay, how many grams of this stuff? So what we're going to do is we're going to start with this, and we're going to work backwards. So if I have 0.5 molar solution and 350 milliliters, what I can do is use this to work backwards to figure out how many moles of this stuff I have. And then once I know moles, I can use the molar mass to get mass. All right, so if I have 0.5 molar, that is 0.5 moles of sodium sulfate. And I know it's kind of repetitive to kind of draw the problem and show you my little chicken scratch here, but I show that so that it's not just done. You can kind of see what I'm doing, because if I just click through the PowerPoints and it's just all done, and you can't, maybe you can tell what I'm doing, maybe not. So that's why I do it twice, kind of see where I'm headed. So 0.5 moles of sodium sulfate in 1 liter of solution, or water, which we can assume it's water because these are all ionic solids. So 0.5 moles per 1 liter of solution, that's what 0.5 molar means. And then what I need to do now is multiply by the volume. If I take the molarity and multiply by the volume, I get the number of moles. But it needs to be in liters. 350 milliliters, the decimal is right there. I need to divide by 1,000 or move that decimal over there. So I'm going to put 0.350 liters. Okay, so these two will cancel, and I'm left with moles. This will tell me how many moles is in that solution. Once I have moles, I multiply by the molar mass to figure out the mass of that stuff. Right? If I have 1 mole of that stuff, it would be equal to the molar mass. So I would multiply the number of moles of this stuff by the molar mass of the substance to get the mass of the stuff. And that's what we want. We want how many grams of sodium sulfate are required. So let's see how this works out. So I got 0.35 liters times the molarity times the molar mass, and I get 24.9 grams. So 24.9 grams of sodium sulfate would be required. So what does that mean? If I take 24.9 grams of sodium sulfate solid, I go to the chemical storage and I grab it. I grab a bottle of this stuff. It's going to be solid. It's going to be a white solid. I take that. I measure it. I need to measure 24.9 grams. If I take and measure 24.9 grams of sodium sulfate and put it in 3 and I put it in 350 milliliters of water. So if I do that, I will get a 0.5 molar solution. Let's try that. 24.9 grams divided by 142.06 grams and 1 mole. That'll give me moles per, that'll just give me moles. And then I need to multiply by 1 over 0.35. I'm just checking to see if this gives me a 0.5. If I were to do this, so 24.9 divided by 142.06 divided by 0.35. I get 0.5. Well, hallelujah. All right, so if I take, so I'm just back checking my work. So if I have 24.9 grams of sodium sulfate and I put it in 350 milliliter solution, for sure we get 0.5 molar solution, or half a mole in every liter of that solution. Awesome. I like this stuff. This stuff's cool. What volume of 1 molar KNO3 must be diluted with water to prepare 500 milliliters of 0.25 molar nitric? So I do this stuff all the time. If I need to make a solution, let's say if you guys are going to do a lab and you need 0.1 molar nitric acid, okay? So every student needs a beaker with 50 milliliters of 0.1 molar nitric acid. I go in my stock room and I've got a bottle that says 12 molar. All right, so if it says 12 molar nitric acid and each student needs 0.1 molar nitric acid and you need 50 milliliters of it, the question becomes, how much volume do I need of the concentrated 12 molar to make that? I do it all the time, and it gets old, but that's kind of what we're doing here. So what we're going to do is we need 0.25 molar nitric acid and 500 milliliters. All right. The formula for this is called the dilution formula, and it's only used for dilution, where we're diluting something. And usually you'll see that word diluted in here. We're not going to use this formula for stoichiometry. Okay, so M1 V1 equals M2 V2. And again, this equation is used for when I have a bottle of something. I have 1 molar nitric acid, or 1 molar, this is potassium nitrate. So if I have 1 molar potassium nitrate, how much water do I need to add that to make 500 milliliters of this stuff with this strength? All right, so it's not stoichiometry. All right, it's a dilution problem, so it's different. So M1 V1 equals M2 V2. M is the moles per liter, or the molarity, times the volume in liters. And so that's moles. They cancel out, right? And then over here it's moles per liter times liter. And so it's moles. And basically this equation just says that the moles doesn't change. Then the total number of moles of the substance doesn't change. You're just mixing it with, you're just watering it down. All right, so let's try it. M1 V1 equals M2 V2. So I take, and you can assign these arbitrarily, okay? So I'm going to say that this is M1. So that's my M1 right there. V1 is what we do not know. So I'm going to leave it as a variable, V1. You can put X if you like, but it's something that we don't know. And then M2 is going to be this one, 0.25. It's going to be M2, and then V2 will be our volume. If you use 500 milliliters right here, then your answer will be in milliliters. But if you convert this to liters here, if you put 0.5 instead, liters, then your answer right here will be in liters. So just, you can do it either way. You can provide your answer in milliliters or liters. Just make sure it's consistent. Okay, so whatever. So if this is in milliliters on this side, then the answer for V1 will also be in milliliters. So we just got to recognize that. So we get 125 milliliters. All right. How did I solve this? Let's look at that. So I've got 1. So that's 1 times V1, or just V1, is equal to 0.25 times 500. I multiply those out. I get 125. Okay, now this was easy because this was a 1, but if this was a 7 molar times V1, we would need to divide by that 7 in order to get it by itself. We'd have to solve it like an algebra problem. All right. All right, let's look at some of our types of reactions, and we'll wrap this up. So there are different types of reactions. In regular chemistry, you talk about decomposition reactions, synthesis reactions, single replacement reactions, double replacement reactions, and combustion. So this is what we see in regular chemistry. So we'll talk about these. In AP chemistry, there's redox reactions or oxidation reduction reactions. There's acid-base reactions. And then there's precipitation reactions. So really, there's kind of 1, 2, 3, 4, 5, 6, 7, 8 types of reactions, some of which are covered in pre-AP or regular chemistry. And then for AP chemistry, these are kind of our main 3. And the reason for that is redox reactions include several of these. So these 2 are redox reactions. Single replacement, also redox reaction. Double replacement is precipitation. And then a combustion, I got to think about it. CH4 plus O2 is CO2 plus water. I guess that's kind of a synthesis reaction. +4, -4, +4, -2, 0, +1, -2. I'm just checking something. Yes, this is a redox reaction also. So notice that most of them can be categorized as a redox reaction. And so that's why there's fewer of them. All right. Decomposition reactions. Decomposition means breaking down. So reaction where a compound breaks down into 2 or more elements or compounds. Usually you need something like heat or electricity, electrolysis, or a catalyst. A catalyst is something that speeds up the reaction or allows it to happen. Usually it's some kind of chemical. And so you add that and then the reaction happens. Okay. So a reaction breaks down. Our baking soda lab is going to be one of these. Baking soda is HNA. Let's see. NaHCO3. That's the formula for baking soda. We're going to heat this guy, and he is going to break down. And he is going to make one of 3 possible reactions. Okay, so we'll have to look at that. So you heat this guy, he'll break down into some kind of products. All right, and so that's a decomposition reaction. A compound may break down to produce 2 elements. All right, so molten sodium chloride is electrolyzed. So if I take sodium chloride, and when we mean molten, I want to say we mean liquid. So it's so hot that it's liquid, it's melted. And so you take that guy, you add electricity. Okay, and what you can do is you can separate those elements into solid sodium, and this is going to be Cl2, and it's going to be a gas, and then you're going to need 2 of these to balance it. That's going to be a 1 there. And so this is the reaction for molten sodium chloride being electrolyzed, or it's molten, so it's liquid and it's melted. You add a little bit of electricity and it'll break down into its component elements. It's actually hard to split elements out of a compound. It's pretty difficult. Okay. A compound may break down to produce an element and a compound. So if you take hydrogen peroxide and you add, I'm trying to remember what you need to add to this. This is called the genie in the bottle reaction. I'm trying to remember what you need to add here. Maybe manganese dioxide as a catalyst. You add, you take a bottle of H2O2, you add this to it, and then you get a lot of smoke. And so it's called the genie in the bottle because it makes a bunch of smoke come out of the bottle. So it's broken down into water and oxygen as an element, so as a gas. So that makes a lot of steam. A compound may break down to produce 2 compounds. So if you have magnesium carbonate, you guys saw this one on the test, magnesium carbonate, MgCO3. CO3 is the carbonate ion. Magnesium is a +2, and carbonate is a -2. Okay, +2, -2. So when it breaks down, if you heat it, so we can write heat here, or another way that we usually show it is a triangle. If we show that symbol delta, the triangle, it means that we're adding heat, and it'll break down. And then calcium carbonate will do the same thing. You take that, you add some heat, you'll get calcium oxide and CO2. And so you can break it down into 2 different compounds. So this is decomposition. Hydrogen peroxide decomposes into water and oxygen. So let's write that. Hydrogen peroxide is H2O2. I'm trying to remember. I think you're going to need some magnesium dioxide, and you can get some O2 and some H2, which are both can be gases, and they're both going to go out of the bottle. Sulfurous acid decomposes into water and sulfur dioxide. Sulfurous acid is H2SO3, and it's aqueous. We'll talk about naming that later. So I'm going to take this and break it down into water and SO2. All right, and then we could balance it, but I'm not going to balance it, but that's what we would get. We would decompose it. It doesn't say how it would decompose. I'm not sure, but there's probably a way to get it to decompose into water and sulfur dioxide. It's a weak acid, so this one, you put it in water, it'll break down into water and SO2, but then it'll reform this back. So this is a weak acid. If it's an acid, but it's not one of our 7 strong acids, it is therefore by definition a weak acid. There's only 7 strong acids. Carbonic acid decomposes into water and CO2. Oh, this is a cool equation. Carbonic acid is H2CO3. It's essentially the carbonate ion with hydrogen. You put that together, you need 2 hydrogens to balance the charge. So that's why it's H2CO3. This guy will decompose, that's a double arrow there. This guy will break down into water and CO2. Okay. They actually add carbonic acid to your soft drinks so that it will make the CO2. And that keeps your CO2 dissolved. Otherwise, all that CO2 would form a gas, and it would all be in the gas phase above the solution, and it wouldn't dissolve in with the liquid, making it nice and bubbly and carbonated. And hence why we call it carbonated. Carbonic acid. Carbonated. Cool, huh? Hydrated salts decompose into salt and water. So if you've got a hydrated salt, this is what we call a hydrate. It's got the dot here. So that means that sodium carbonate has water molecules attached, which is why we call it a hydrate, because it's got the hydration sphere, so it's got a water molecule attached. If you heat this a little bit, it will make that water leave. And so you're going to have this plus the water. Okay. And I believe I put a question about a hydrate on the test, so we'll go over that at some point. Maybe next week, maybe Friday if we have time. I find that it's hard to do much because there's so much limited time. All right, I'm going to stop here because this is a lot. So next we'll cover synthesis reactions, and we will continue. That's it, guys. Thank you.